Yeah, welcome guys. In this video, I'm going to teach you how complex numbers came into the world of mathematics. It is one of the mysterious thing I've ever seen while growing up, while when I entered college, or let me call it university. Because when we were in secondary school, when we were in primary school, in elementary school, we were told that um, if you add something like this 2 minus 3, which we all know is a negative number, but then we were told that 2 minus 3 will give us minus 1. We know fully well it's going to be minus 1, but they told us then that it will not exist or it's impossible, maybe probably because of the knowledge we have then. Okay, now immediately we get to university, into secondary school, which is our high school, we were told that square root of a negative number does not really exist, right? So if I write something like this in secondary school, a square root of any negative number, immediately we know that it will not exist. Why? Because we were told that way. We weren't given a genuine reason why it was like that. Okay, but immediately when we get to university, everything changed. Let me show you what bets complex numbers, what really came, what gave us the idea of what complex numbers are. Now, there was this mathematician called Cardan. Okay, he was solving a particular problem, and here is the problem. The problem is um excuse me, the sum of two numbers. So the sum of two numbers is 10. Let's just say the sum of the two numbers is 10, right? And he said their product is 40. Their product is 40. Find the two numbers. So how do we go about this? You all know fully well that from this equation 1, what we are going to do is just to make x subject of formula. Okay, so we have, or probably let's say y. Okay, so let's say y equal 10 minus, excuse me, sorry, this should be neat. I don't want it to be rough. Okay, this should be 10 minus x. This is 2. Okay, this is equation 3. So from here, if you put 3 into 2, put equation 3 into 2, we are going to have x into bracket 10 minus x equal 40, right? Cool. So from here, if you multiply out, we're going to have 10x minus x squared equal 40. Okay, so what's the next thing to do here? So we are going to have 10x minus x squared equal 40. If we collect like terms, or we rearrange it, let's say we have minus x squared plus 10x minus 40 equals 0, right? From here we can just have it as, if you multiply through by minus -1, we are going to have x squared minus 10x plus 40 equals 0, right? Okay, cool. From here we have to solve this quadratically. Looking at it, is not factorizable. Using the quadratic formula, we see that the quotient of this here, our a, which is 1, this is our b, right? This is our a, this is b, and this is c. Swapping it, we are going to have x equal, oh sorry, minus b plus minus square root of b squared minus 4ac all over 2a. So how do we solve this? How do we solve this? We'll see that, okay, we're going to have x equal, our b is minus 10, minus times minus, that's positive 10. So we have 10 plus minus square root of b squared. What's our b squared? 10 squared, that's 100. 100 minus 4ac, 100 minus 4ac, And what is our 4? Okay, sorry. So what's our 4? We have 4, excuse me. A is 1. Okay, cool. And we have C to be 40. Okay, all over. So we have 2 times 1. So we have x equal 10 plus minus 100 minus 80. I say 100 minus 60, or 160, sorry. So we are going to have root negative 60 all over 2. And this was the problem that Cardan really solved. We are going to have two problems, x, or two solutions. X is going to be 10 plus root negative 60 over 2, and we have another one, x. Okay, let me call this x1, call this x2, which is 10 plus root negative 60. Sorry, that's going to be minus, excuse me, minus root negative 60 over 2. Now, the truth about this thing is that Cardan doesn't even know what this number negative. He was not sure of what this thing could be. Was not sure of. Could this really exist? Negative, a square root of a negative number. But one thing he knew that when he add them together, when he add x plus y, do you get that? Okay, uh we just got x. You can really replace it. Don't forget y equal 10 minus x. So that will be, for the first one, we are going to have 10 minus, do you get it? Do you get it here? So what Cardan did was that when he added the two numbers together, he saw that they are giving him 10, and when he multiplied the two results together, they are giving him 42. So he was surprised that how can you have root minus 60, negative of minus 60? Is it possible? Now, and that was where the idea came from, like, oh, like, okay, how do we solve this kind of problem? That is where he led to something like this, that you can really write this thing as root negative 1 times root 60, right? So, and they replace this root negative 1 as I, and it was Euler that first used this in notation for I, or for complex number or imaginary numbers. Okay, so he represents with I, and immediately he used I. Scientists, mathematicians started having interest, like, okay, what is going on with these numbers? They now extend this thing to what we really know as complex numbers. Z equal a plus b root negative 1. Okay, where root negative 1 is I. So basically, Z equal a plus bi. This is where the idea of complex numbers comes in. Can you see? In fact, it is a superset of real numbers. In actual sense, if I write a number 2, I can write 2 as sorry, I can write it as 2 plus 0i. I can extend it to the complex field, right? It is, the complex numbers they're expressed in plane, right? So we have 2 plus 0i, and any in actual sense, any real number is a complex number. Any real number is a complex number. So when he did all this, it led to the idea of dealing with I. If you see my thumbnail very well, you saw that I wrote iota squared makes it real. So what do I mean here is that if I square this number, if I square it, I'm going to have iota squared equal negative 1, right? Iota squared equal negative 1. So which means if you square that, you are going to get a real number, right? So let's focus more on how complex numbers are, how they work. Now in the comment section, please kindly solve with the idea of what I've taught you so far. Solve this for me. The first answer will be rewarded. Minus 16 in times root minus 25. Let me know what this be in the comment section. Let me know what this be in the comment section. So let's continue. Okay, so I said earlier that iota squared equal -1. Now, what if we multiply both sides with iota again? I'm going to have, or let me just call it I. So we have I squared times I equal -1 times I, right? So this is I cubed equal minus I. So note this. This is another thing we need to take note of, right? Okay, I cubed equal minus I squared equal -1, right? So just keep noticing all this. Now, if I multiply this by another I, I'm going to have I raised to power 4 equal minus I times I. Don't forget, I'm multiplying this by I, multiplying this by I. So this is I raised to power 4 equal minus iota squared, right? So basically, don't forget that iota squared is -1. So I'm going to have -1. So that means iota raised to power 4 is 1. Iota raised to power 4 is 1. Can you see this? So we have this, and the first one. Basically, we have I. Basically, now the second one is what? -1. The next one is what? Minus I, and the last one is what? 1. So what we are saying in essence, if you notice very well, you see that the complex is cyclical. The complex number is what? Cyclical. The result, it will not go beyond this value. It will not go beyond this value, right? It will not go beyond these 4 values here. So let's see, there is this thing you need to understand. What if you have numbers? How do you deal with numbers with a higher power of I, something like this? If I have I raised to power 5, how do you do it? I raised to power 5, it's, anything greater than 4, you can easily uh do the value, or get it simplified. Look at this. This is going to be iota raised to power 4 times iota, right? And iota raised to power 4 is 1, right? So this is iota. So basically, iota raised to power 5 is iota. So what if I say iota raised to power 27? Now, in essence, what I'm saying in essence is that every multiple of 4, every multiple of 4 is what? Every multiple of 4 gives 1. Okay, so now iota raised to power 27, what is the closest multiple of 4 relating to this? That's I raised to power 24, right, times I raised to power 3. I raised to power 24 is 1, so remaining iota raised to power 3, and I raised to power 3 is minus I. Can you see? A lot of them. So let me just do an a simple overview of what I've been talking about since. Basically, my remarks so far in this short video I am making for you is that the square root of any negative number n, say we have number n, the square root of any negative number n, so I have something like that, like this, the result is the same thing as what? Root n I. Okay, so this is a remark of what I've been talking about since. Do the question I gave to you. See you in my next video. Thank you for watching.